In this question, we've got some sort of nested circles. We start off with circle C1, and the radius of this circle is 1. The way that each circle is linked to the next circle is by drawing a tangent of length 2. So tangent of length 2, and the ends of that tangent lie on the next circle in the pattern. The question is, if circle 1 has a radius of 1, what is the radius of circle 100? Well, this is a really nice question, and part of our thinking should be, obviously we're not going to do 100 of these, so there should be a pattern if we do 2 or 3, and it will become obvious. Let's just try it out then and see this pattern. So if we first of all think for circle number 1, its radius is 1, and the tangent has length 2. Well, thinking a bit about that then, if we try and draw a sketch for ourselves, and we'll just draw the top half, because this is a nicely symmetrical problem, however we want to draw it. We can just draw the top half, and we can just actually draw, if we want to, half of this tangent as well. The tangent has length 1. The radius of the circle is 1, so this side will be 1, and this will be 1. And a really, really important fact for us to remember now is that a tangent and a radius must meet at a right angle. So we've got 1, 1. This is a very famous triangle, and obviously by Pythagoras' theorem, 1 and 1, this side has got to be square root of 2. So what we've got is we've got for the C2, or the second circle in our pattern, the radius has to equal the square root of 2. Now let's try and repeat then for the next circle in this pattern. So we can draw another picture. And this time we're imagining C2 is our inner circle. So for C2, the radius is root 2. And this time when we draw our tangent, we could draw both sides of it. It will have total length 2, or we could just draw this side which has length 1. It doesn't really matter. Again, when we join it back up, we've got a right angle triangle, radius, tangent. This side was root 2, this side was 1. So when we square it, root 2 squared is 2, plus 1 squared is 3. The hypotenuse will have to be root 3. So now we've got C3, and the radius of the third circle in the pattern will be root 3. C3 is obviously this outside circle, which I'll draw in a dotted line, and you can see where C2 came from before, well, because it would be that with the dotted line. So our radii at the moment, we had C1 with a radius of 1, C2 was root 2, C3 was root 3. Shall we just try one more to check the pattern, and then we'll probably be happy that this is what's happening. So again, we can draw a circle, half of our tangent, which will be 1, and actually here, let's take our root 3, but we can sort of see this generalising if it was any number n at the moment, root n. Always going to be 90 degrees. Root 3 squared is 3, plus 1 would give us 4, so we'll get square root of 4, which we know is just 2, but it might be more helpful for us to leave it as the square root of 4. So we'll have C2, C3, C4, where R is the square root of 4. Should we just see what happens in the general case to finish off? If we've got a circle where we've got square root of n, we'll have 1 for half of our tangent. You can see exactly what's going to happen. Square root of n squared gives us n plus our 1 squared. So we'd get c n plus 1. If this was cn, cn plus 1 will be the square root of n plus 1. We can see exactly how that works then. Each time C4, root 4, C3, root 3, C2, root 2, C100 has got to be the square root of 100, or we would prefer to just write that as 10 for our answer. So 10. A really nice problem then, where actually you just had to look at a few steps and you see this pattern.